Guys, we're back with yet another video on carbon and its compounds. This is Abhinav here, and you're watching Chemistry of Carbon channel. So, today we're going to look at some more topics which are very interesting and are the basics of organic chemistry. So, we covered organic compounds in the previous session. So, today we're going to look at saturated and unsaturated hydrocarbons. Yes. So, what are saturated and unsaturated hydrocarbons? Saturated hydrocarbons are all the hydrocarbons that have only single bonds between carbon atoms. So we call them as alkanes, and they have a general formula CnH2n plus 2. Let's put n equal to 1. So we get C1H 2 into 1 plus 2, which is CH4. Yes. Now, if we look at unsaturated hydrocarbons, they have double or triple bonds. It is not just one group, it can be double or triple bonds. So if it's double bond, they're called alkenes, and if it's triple bond, they're called alkynes. Alkenes have the general formula CnH2n, and alkynes have the general formula CnH2n minus 2. So for that, let's just understand it like this. So let's say we have ethene, because methane is not possible because carbon having double bonds hydrogen is not possible. And why is ethine not possible? Same thing, but C1H2 minus 2, which is C1H0. It's just C. That's not possible, right? That's why methane is basically not possible. Let's see ethene and ethine. So ethene is just a double bond between the C and hydrogens implied. So it is C2H4. Ethine has a triple bond, and the hydrogens just imply. So, what about alkyl groups? I'd have heard of alkyl groups earlier. What is that? Let's say we have alkane. So, let's say we have an alkane. Let's say alkane is A. So, when you minus the H, you get an alkyl. So, let's say we have methane. Let's just keep it as CH4. If you remove the H, it will be methyl. Okay, now, so this is just a table of alkanes and alkyls. So methane, ethane, propane, butane, pentane, hexane, heptane, octane. Now, met, eth, prop, but, pent, hex, hept, oct on deck. They're known as the compound roots, or rather word roots. They're known as word roots. And the thing is, these are always substituents. They can be just like CH3, CH2, and CH3. And in common names, we name them using these. But generally, in the IUPAC name, we call them as This is called propane. So now we look at another type of we look at isomerism. Yes, this is a very interesting topic. Why? Because we're going to understand this using an analogy. Sounds fair? Yes. Now let's take some. There are some kids here. Let's just assume that there are some kids here. Let's say we have the kid's name is Carbon. So Carbon has to join hands with his twins, they're also known as carbon, such that they can form different patterns. Yes, they can form different patterns like these, and in the end, the number of carbon should be the same, and they have to keep, they have to hold, like they need other carbons or hydrogens to hold their hands, such that each child is holding on to four other people. Just like how in carbon we fill the four valence, the octet, by you giving four valence shells. So same way, they need to hold each other. Now there can be different ways of filling them, right? So this is known as isomerism. Scientifically, when we relate it to carbon, it's known as isomerism. Now, can we divide into structural isomerism or stereoisomerism? We'll not look at stereoisomerism for now. We'll look at it in another session. Then structural isomerism can be divided into chain isomerism, position isomerism, functional isomerism, metamerism, and automerism we will not look at right now. So, when we look at structural isomerism, they have the same molecular formula, but the way they bond is different. Yes, in throughout isomerism, we'll have the same molecular formula. That's what isomerism basically means. Now, we have a good example here, butane and isobutane. So, butane is, there are four carbon atoms here and all the hydrogens. Now, isobutane, now the thing is, if we have any number of carbon atoms, yes, and we have another carbon here, then its common name would be iso, and count the number of carbon atoms: one, two, three, four. There are all single bonds here, so it will be whatever will be the word root for that number of carbon atoms. So but, single bond, so ane. This is how it works. This is the common name, but the actual IUPAC name which was given is just write it here for you. 2-methyl butane. Actually, it's 2-methyl pentane. Sorry, 2-methyl propane, 2-methyl propane, or ideally it is just butane or N-butane. N-butane. Yes. Now, chain, these are just the different forms of structural isomerism. So we look at chain isomerism. The parent chain is different. The parent chain is just the longest chain. So if we have carbons like this, we'll not choose this as the chain. That's wrong. The real chain will be this. This is right. So we looked at one example earlier, butane and isobutane, pentane, isopentane, and neopentane. So pentane, we have 5 carbon atoms like this. Isopentane is when we have 4 carbon atoms as a chain and 1 carbon atom like this. This will be the methyl group. And neopentane, interestingly, is only 3 carbon atoms. And we have 2 methyl groups on the same. So this will be 2-methyl butane, and this will be, let me write it down here, 2 comma 2 dimethyl propane. And because when we have 2 methyl groups attached to the second, we call it neo. This is the common name. Now let's look at position isomerism. The position isomerism is just the position is different as the name suggests. Now if we have butane 1 all and butane 2 all, so we have, so butane is just 4 carbons, the same thing here. The hydrogens is implied, so the OH can be here, yes, or it can be here. And functional isomerism is when the functional group is itself different, but the molecular formula is the same. Example, ethanol or ethyl alcohol and methoxymethane or dimethyl ether. Now, e- let's just see the structures of ethanol and methoxymethane. So ethanol is just CH3 CH2 OH. What about dimethyl ether or methoxymethane? It will be CH3 OCH3. Yes. Now you see that both have 2C, so C2 H3 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 H2 H, so H3 plus H3 H6, and both have O, so C2H6O. You see they have different functional groups altogether. The group is different but still the same structural, the same molecular formula. Now metamerism is like it's almost the same as positional isomerism. We look at an example. The distribution of carbon atoms or alkyl groups is different with reference to the functional group. So methoxypropane and ethoxyethane, or can be methyl propyl ether and diethyl ether. So methoxypropane is just CH3O, CH2, CH2, CH3. That's this. Now, if we look at ethoxyethane, which is simply the same thing, CH3, almost just going to be like this. See, ideally, it's just the oxygen is in different places. So this is known as metamerism, and it's very similar to position isomerism, as we can clearly see. Now let's look at organic compounds. Yes, we saw organic compounds. Now let's look at how they are divided, their classification. So organic compounds can be acyclic or aliphatic compounds. Basically chains or branches, examples alkanes, alkenes, alkynes. Straight or branch chains, still didn't like if you still have problem finding it out what does straight or branch mean. Straight is just one proper chain, or it can even be like this. This is also a straight chain, but branched is in the middle there's another carbon. Yes, this is branched. Now, what about cyclic compounds? These are basically rings. We have seen rings like this. Yes, basically in compounds, it could be like this. It could be like a triangle. It could be like a hexagon. Yeah, this is a cyclic compound. Can be divided into homocyclic or carbocyclic and heterocyclic. So alicyclic compounds are basically just single bonds in the chain. Yes, like this, and then the hydrogens just imply. Generally, all carbons will have two hydrogens, and that's why alicyclic compounds and alkenes are generally isomers. Aromatic compounds, aroma. Yes, we have heard of this word a lot of times. So, aromatic compounds are those basically which have aroma, but they are rings of benzene. Benzene, very important compound in organic chemistry. In fact, we have a separate nomenclature for benzene itself. So it can be benzene. If you like add two benzenes together, it could be naphthalene. There are various compounds. Heterocyclic is, let's say we have benzene. So let's just take benzene. Okay, let's just draw benzene like this. Yes, we have benzene like this. Now, let's say instead of, and there are double bonds and single bonds alternating, all are hydrogens. Let's just draw all the hydrogens for now. Now, let's say we have this carbon and hydrogen. Instead of these two, we have a nitrogen. Yes, three. So nitrogen can take its place. Now the compound is not exactly benzene anymore. It's a different compound. So this is a heterocyclic compound. Hetero. We'll understand what it means soon enough. So we discuss these things. Now, do we, like, we named it, but do we have a systematic way of naming all organic compounds, or is just some common name we have to follow? We do have a systematic name. In 1949, an organization was set up to formulate the rules for naming organic compounds. The organization is IUPAC, IUPAC, called like that. So, International Union for Pure and Applied Chemistry. So, prior to this, the organic compounds were known by their trivial or common names, which generally indicated their source. We have two examples here. Formic acid gets its name from formica, which is Latin for a dance, and acetic acid, which gets its name from acetum, which is Latin for vinegar. Acetic acid is 5% of vinegar. And one more thing, why is systematic nomenclature even important? It's important because we don't require unambiguous names for all compounds. We need a systematic name which we can go throughout the world, we can use that name. So that's why we need systematic nomenclature. Now you're talking about this compound, we saw the structure, it some structure which looked like this. Yes. Now, what is the C6H6? We know carbon atoms is equal to hydrogen atoms. They are in alternate single, double bonds. Now, what is this? Ideally, this is benzene. Benzene. Now, what are all these three things? Are they all benzene? Yes, this is benzene, this is benzene, and this is benzene. Why these two? We'll look at it a little later, but this is the bond line formula of this. This we'll not look at now. And this is an aromatic compound. So it comes from the word aroma, just as the word suggests, and it's a very important compound, benzene. A lot of compounds. In fact, benzene is a common name, but when we use it for IUPAC nomenclature, because if you look at it, the IUPAC name of this compound would be really large. So instead of using that, we just use benzene. Now, functional groups. Yes, functional groups. Before understanding functional groups, or what we have been calling things functional groups earlier, let's look at what is a heteroatom or hetero. Any atom that bonds with hydrocarbons other than hydrogen and carbon are called heteroatoms. So we have C, let's say we have C here, C here. Now, instead of CH3, we could have C with O and an OH or an H or a H. Could be anything, right? So those atoms like SON, OH is a compound, hydroxyl, they are heteroatoms. Now, carbon could just form OH like this, or there could be another CH3 with it, and it will form CH, increase in CH2. So this group is called functional groups. So this is known as, like, let's see some examples. Ketone is an example. Let's say we have carbon, 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 and in the middle there's a double bond with oxygen. This is known as ketone group, and it can be any group. Yes, it's variable. Alcohols, let's see it here. So carbon, carbon, and that could be OH here. Now the thing about alcohols is that it can be at the carbon in the end, or it can just be in the middle, whereas ketones are always in the middle. Aldehydes are always at the end and have a double bond with oxygen and a het, a hydrogen. Yes, this is aldehyde. Now, what about halides? Halides are basically halogens, are all chlorine, bromine, iodine. Yes, these halogens, they take the place of hydrogen. Let's say we have hydrogen, drawing it for this purpose, and now a Cl comes and basically you can say it displaces it because it's more reactive. It takes its place and removes hydrogen. Yes, so it removes hydrogen and now it becomes chlorine. So this is basically known as substitution reaction in organic chemistry, and this is the halide group, and they are always substituents. They are never considered as a direct functional group. They're always called substituents. Next, we have carboxylic acid, the most common acid in organic chemistry. So this is always in the end too, and these are known as terminating functional groups. Aldehydes, carboxylic acid, they're known as terminal functional groups, terminating functional groups. So the last carbon will have a double bond with O, same as uh, aldehyde, and they have OH, not a H. OH, not a H. Now let's look at homologous series. Now, we'll just see the definition first. So, a homologous series is a series of organic compounds which have same functional group and similar chemical properties. So, each member of the series differs by CH2 in its molecular formula and 14 units molecular mass. So, this is just a table. We'll understand these 4 points right now. Yes, so let's just take, we have, let's say, ethene, because we just saw, let's just see ethene, and we have the hydrogens like this. For this purpose, I'll just draw the hydrogens. Let's say these are all hydrogens. Now let's say another group, CH3, H, H, H. 1, 2, 3, 6. C3H6. What is this? 1, 2. So C2, 1, 2, 3, 4. C2H4. C3H6 minus C2H4. If you remove it, it will be CH2. So, like this, even for alkanes, we see that it differs by CH2 in its molecular formula. Now, why 14U? Carbon has 6 protons and 6 neutrons. So, both protons and neutrons are 1U. So, 6 into 1 plus 6 into 1, which is equal to 12U. And hydrogen is just 1 proton, which is equal to 1U. Now we have to multiply that by into 2 because we have 2 hydrogen CH2, which is equal to 2 units. 12 units plus 2 units is just 14 units. Yes. Now they'll have similar chemical properties because in all these compounds, organic compounds, adding a methyl group and removing a hydrogen is basically just like adding a part of it to it again. So the chemical properties will be the same because just carbon and hydrogen adding, there's no other oxygen adding or no extra double bond, it's just normal single bonds. Yes, but there may be change in physical properties. The most major change in physical property is mass, melting and boiling points, melting point and boiling point. And then we also have these things that members are represented by same general formula like alkane, alkene, alkynes. Even alcohols have this general formula CnH2n plus 1 OH, and they show gradual increase in their physical properties or gradation. Now, there's one more point I'd like you to know is that members can be prepared by general methods. Now, this has been found out experimentally, and we cannot just find it out without using experiments. So, thank you guys. Hope you guys enjoyed the video. And if you like the video, do hit that like button, subscribe to the channel if you haven't done so already. Share it with your friends and family so that they can be benefited from it. And do comment on the comment box below. Thank you.